up there, I want to introduce you to somebody. Matt, are you here? Matt's 17 years old, and he's quite bright as an individual. And he's going to run what he's built for you, his Tesla coil here, which is excellent for somebody that's 17 years old. You're all going to be jealous when you see this run. But here's Matt, and at 17 years old, go on to college, Matt. Learn all this. Okay, first of all, thank you, Eric, Eric's from the groups, for building this machine right here. So, come up here, Eric, where are you? So anyway, Eric has built this machine. He built several machines. There were a few problems with the machine. It was supposed to be 16 poles. But what we found and what you will find is that if you get the magnetic fields that you see here too close together, when the coil goes to pulse it, it'll interfere with the next magnet, slow down the machine, and then it won't gather any of the charge. So all my machines that have to do with 3 coils and bipolar switchings are all self-starting machines. So if you hook them up, they start themselves. This one here is kind of a little bit different. A lot of people have asked about this machine, so I thought that I would put on the board and let you take a picture of it and walk by and look, as long as you don't stay up here too long. What my thinking was and why I did it this way in a tri-magnet arrangement. Okay, when I built this machine, I needed a scale model, and I could only find, I didn't have enough time to get an aluminum wheel made. Anyway, the magnets on this machine make up a special magnetic pole because I'm looking at something, because I want something to attract in, and I want something to push out, and then I want the energy to get collected in steps, and then at the precise moment, I want to dump the energy. So what I did was I took some ferrite magnets, number 8s, Briggs & Stratton magnet that's in the flywheel, and I arranged them this way. What I wanted to do was I wanted to make a pyramid type field. Sort of like that. Can you see that? And I wanted the south to come around so that they would be in between these poles. Because there's no metal here. There's nothing to attach it to. It's a Harbor Freight wooden wheel, which I put on the mill and I was able to mill it round this way, but I was not able to go this way. So don't be afraid of it. I wasn't. I wanted the magnetic fields to do this. I wanted a concentration in the north, and I wanted the South Pole to wrap around and be right here. Anyway, that's what I wanted in the shape of a field. So I arranged the magnets to do that, so that they would bounce up sort of like this, and these would bounce out through the wood this direction. And I wanted to do that because I could not control the magnetic field coming from the coil. So I wanted to pinpoint it on the magnets, and I wanted it to be able to self-start and accelerate. Eric's was no problem doing because he has a big magnet here. And once again, you'll see on the back of these magnets that the one magnet's angled so that the South Pole on this is concentrated to come out. And so you use the Neo magnet on the backside. Anyway, so when we do this, we can make a really sharp, and this is what I'm going to say again, is I am looking for the fastest collection process. And sometimes with the fastest collection process, you must pay attention to all the physical laws that apply to normal electronics. Because there's no free lunch without any work to it. To get the free out of it, you have to put some work into it. So what I'm looking for is a motor pulse that sort of comes up and goes up like this, and then comes back down like that. And this is the part that I'm concerned with. I'm concerned with the pulse, keeping that pulse as narrow as possible for the most amount of power in one push. So you can see the way Eric starts, not a real lot of power, but once the mass is rotating, it's multiplied by the pushing force times the distance of this arm out. So he does have quite a bit of torque here if you torque from this point. So he can run a water pump, pump water all day long in a field, not burn very much energy, and then take his batteries back to his car and start them up. He could do that. He could also take this output and say, I don't have this battery, and put it back to this battery. Why? It's capacitive discharge. It's the same energy when it ends up in the battery. So whatever this energy is, whatever the radiant does over here, it's stored in a capacitor, and when the capacitor reaches a certain level, you see this flash. I don't know if you all can see this flash. Can you? Okay. Everybody said, well, what's doing that? Right? A stair-step comparator, analog. Now, what do I mean by that? Some unknown term. Tom Bearden said a long time ago you could run a battleship if you could just take little impulses from the battery and build them up in stair steps to charge something and then dump it. So what I'm looking for from this is I already know how many pulses I have. So since I have this trigger taking place that's going around on this coil, I already have a frequency, don't I? So it makes no difference to me what that frequency looks like, because I'm going to use that frequency to trigger my comparator to stair step it up. And then the comparator is going to look at it and say, No, this isn't high enough. Nope, this isn't high enough. Nope, this isn't high enough. So you might see 3 stair steps up and then bang, a big discharge. And you can set this comparator because it looks at the capacitor voltage. So it watches the voltage as it goes up, and then the comparator says switch polarity optically, hit the driver, and the driver fires the MOSFET. Now I talked about this on the group. I said if you're going to do this, you had to develop a way to follow the capacitor instead of what normally was discussed, an SCR and a diode. That's not the same thing. You cannot keep a constant control of what that device is going to do. So I wanted everybody to understand that the circuit that I developed was for a specialized application that just watches the capacitors and then decides, depending on what I choose to set the comparator at, to drop that capacitor to a low impedance load. Well, that's a problem because some just think that you can just drop that capacitor right across this battery, which looks like something like 0.00023 ohms. So we all made a mistake once in our life of taking the device, the transistor, and putting its emitter, thinking that when I drop this across here, I'm just going to get the power across the battery. But that's a mistake. So I don't want you to make that mistake. So I'm telling you about the mistakes. The mistake is you cannot drive the load with that into the battery. It looks good for a few minutes, it maybe runs for an hour, and all of a sudden, second emitter breakdown. It vaporizes right here. So, the solution to that problem, and you'll see why I do it and why I call it inverted and why I make the circuit invert, is you take the battery that has that impedance, known, can be measured out, you'll find out it's real low, unless it's sulfated, then it's real high. The solution is to potentialize the battery with V voltage. No current, there is no current yet. The next solution is to use something that has a drop in it that's very low. That would be the FET. That would be the RDS on. So anyway, the FET sits down here inverted. With the ground potential. So what happens is you potentialize this with the voltage. The capacitor rises up in stair steps just like this and then goes bang. That drops the full capacitor across the battery and gives you gain. Now, why do I say that it gives you gain? Because this is nothing more than a common amplifier. If I choose to put audio signal in here and winding out here and bias this device correctly, I have a gain in my audio. I've amplified what I wanted to do. So what is it that I'm looking for to amplify? Anybody? Power. I want the power at a certain gain. So I drop this across here, I put a current meter up here, and all of a sudden I find that I don't have 1 ampere, I don't have a half ampere, I don't have a milliamperes. I have 360 amperes for that amount of time. And I keep doing that. You can put the current probe there and find that. It looks like 1 amp on the meter, but when you put the current probe there, you find out it's over 200 because it's instantaneous. So the meter tricks you. You can't tell anything from your meter. You have to use a current probe to tell what's actually going on in this circuit. Okay, here's the idea. The idea is to take an amplifier, plus and minus, basic electronics, 6th year comparators. You choose a reference voltage and you apply it to the amplifier. And that either puts it in this state or this state. Following me? You make one of these so you can adjust it. When you adjust it, you can fire it in any position from here to here, in any of these increments. Now the next thing is to isolate this, and you can do that with a diode and an optocoupler and a resistor. Because you don't want too much to go through this optocoupler that's out here. So now, when the capacitor stair-steps itself up to the point that you've chosen from the divider, which is voltage, it says turn on, and this turns on, and the driver turns on, and this is the important part, driving the FET. Because the FET looks like a big capacitor to it. And that's why they make FET drivers. So John makes his own. What I do, we used to have to do this with a relay. In 1984, we had to do it with a relay because we didn't know anything about what this was. And this all started the 1984 Tesla convention when Jim Watson reproduced the machine. The machine sat on stage, and what you heard when it started up was a push button to start this big jet aircraft motor. And then all of a sudden after that, it was click, 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 click. The relay was just switching back and forth between the capacitor dump and the motor input. And so when the motor was off, the secret to any energy solution in that situation is stealing the surface charge. The motor comes on, gives you a pulse, and it goes off. Then in the next milliseconds, the capacitor is dumped across the battery, just like that. Well, what's the battery do? The battery actually does this, and then you steal the surface charge, and it keeps doing this. What do you see on a capacitor when you're discharging it? Right? So this is the battery. This is the battery level right here. Motor comes on, battery drops. Right? In the next instant, motor goes off, capacitor dumps. Battery goes like this and falls back down. But before it falls down to this point right here, guess what? It's already taken the next on pulse. So what did I steal? I just stole this surface charge, and the battery continued to be the same. And that is the best explanation I can give you. It's the simplest explanation I can give you on what is actually occurring. Now, where's the free come in? Does anybody know? Don't be bashful, get up. Right? Watson could steal the mechanical energy all day long. And so can the SG if you do it right. So what did John do? I couldn't produce the 1984 machine. I'd already got my letters opened up. I already got threatened on the phone. And I said, what's the best possible thing I can do, since that what was very interesting to me, and I wanted to do it. I wanted to be able to make something and get the information out there, and I couldn't do it because I was told not to do it. In fact, I waited. I waited until the computer, until there was the internet, because before that time, we had the fax machine. And we had people that would tap telephone lines. And now they tap the computer lines. And then when they don't like you, they send you a virus, right? And all of a sudden you have a blank screen. So, technology. Anyway, the best possible thing that I could teach you is if you're going to steal the surface charge, do it correctly. And that way the machine continues to rotate like this until the bearings wear out. They just wear out. Now in Europe in 1984, they developed a motorcycle that had a motor, and the motor was broke up into pulses just like this. Tom Bearden said it very cleverly. Those who know can utilize the Energizer, which is a drag-free generator. So what's a good candidate for a drag-free generator? Is a G-field. Is the G-field generator. Under load it speeds up, and with no load it slows down. But we're going to keep it across the battery. We're going to keep it across the battery at this point. So that's kind of a strange wave. So we turn the motor on, accelerate the motorcycle. This gets faster, faster, faster. These get shorter, 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 but stronger because of the current. And when you get done running the motorcycle, what have you just done with the battery? You stole the surface charge. That was Watson's machine. What happened to the machine after that? No one knows. I have my suspicions. I think they're underground. And I think they're bigger. Because the only way I could sneak this out was to come up with this little toy that everybody named the schoolgirl motor. And then all I needed to do was to get somebody, and Jean, she volunteered. Actually, she was interested. And when she found out that this little girl did this, she had to come and see for herself. And of course, then when the little girl said, "What did you say to the class?" Because Jean wrote the article. She says, she got up and she told the science teachers, "Well, the magnetic spins go this way and then the electricity goes this way," and the science teacher went to sleep. Can't have an Einstein in your class, right? And look better than the teacher. So, but she did, she explained it, and they were not going to give her first prize. They were just going to ignore her, hush hush. But the kids rebelled. And they said, "No, we're voting for this little girl. And we want this little girl to win." So they did. Of course, the science teacher was reluctant because he didn't want his name on this. So they got together as a group in some cafeteria down the other way there and said she could never participate again. And that's how they squash it. What we want to do with this machine is we want to be able to collect the charges, charge up the battery quickly, and there's only one way to do that, and that's with a capacitor dump and the correct frequency and the correct resonance. Now on these machines, you will notice that there's two separation of energies on this machine. There's this coil, and then there's this miraculous thing out here that's just hanging there. Now, one at a time, come up and feel the difference between the two coils. You first. I'll direct this. Feel the big coil and then feel the coil behind it. What about the big coil?
It's cool. Cold, actually.
What's driving the wheel?
Big coil.
Sure. Okay, did we all get a feel of this? Okay, the coils are on the same line. They're on the same set of wires. One has an iron core and one has an air core. And you're saying, why did John throw the coil behind the big coil, right? You're all asking that question. Because we couldn't tune the machine. It's a tuning mechanism to get the machine to run. Eric, do you want to explain that the machine wouldn't run? Here, come on.
That was after we figured out that the magnetic fields are too close. So then we tried it at 12 volts and we could get it to run as an SG. We tried it at 24 volts and it would self-oscillate. So that's when we decided to switch to the Bedini Cole switch to drive the motor, and that sped it up significantly. But it still wasn't running quite as good as we'd like, and that's when we added the second coil.
But we added that second coil to get the energy out of the machine. Because the original Bedini Cole switch, here, come here. You use your hands, right? Did you feel the two? Mm-hmm. What's the difference?
The big one's cold.
Right.
And the small one's warm.
But what's the energy feel?
The cold is more organized, and the hot is unorganized.
Disorganized. Right. That's what happens when the alignment takes place. It takes place that we were talking about. But I couldn't get the energy out of the coil under this motor situation, and I couldn't get the energy out of the coil under this motor situation. So the solution to my problem was to have one organized and one disorganized, and take it from the disorganized one. Compress it and take it, the same way the SG does. Does that make sense to you? Well, if Eric comes up here and disconnects that coil, the erratic move, this here will go erratic, and the motor will slow down. Because it won't align. Now, some of you have tried to build these motors using the Bedini-Cole circuit, right? And some of you can get some energy out, and some of you don't get any energy out, because I watched it. I watched a whole years of internet chatter about John's 3-coiler. And I haven't seen anybody yet get the energy out that's worth anything. That's how you get the energy out, is by misbalancing these two. This does not equal that. So there's two different impedances. And to get the energy out of this, I had to misbalance it. And believe me, it drove us nuts for a little while.
Is that creating asymmetry?
Yeah, exactly. There's a differential between these two, and I'm sucking one of them out. And this is exactly how I'm sucking them out. When we added this, the voltages increased on the capacitor, and they would step upwards. And so the comparator circuit would look at it, and pretty soon, I think we measured it, Eric, it was at 300 amp pulses, where we couldn't even get 50 amp pulses before. That's quite an energy change. And each time this is flashing, that's the comparator signaling the stair-step is at full potential dump. So, you're all saying, show it to me, right? Show me the stair-step. Come and look at the stair-step. See, it's stair-step up and dump. That's a cap dump into the battery. It's the electromagnetic field around the wire every time it dumps it down. So yeah, it sounds like a stuck record player. And it's on Eric's too. And you can always tell a capacitor dump machine if you use an electrode. And the reason this is doing this is because look at the speed of the wheel. So if I slow the wheel down, the comparator knows to take longer to charge the capacitor.
John, would that extra coil help on an SG circuit?
No, it has nothing to do with the SG.
Okay.
This is a bipolar switch.
Oh.
See, there's the capacitor dump, and see it step up.
Mine does it in about 4 steps. But I'm
Well,
using-
Eric's is doing it in 3 steps.
But I'm doing the SCRs.
Yeah. So if I slow this down, the comparator knows to take more time to build up and then dump. Yeah, when you see the red light sort of dim, it's actually off, but it's off real fast and the green's on. That's when the comparator says to the opto, put the bias to the FET to dump the charge on the capacitor inverted. And by the way, that step is being controlled by each magnet that's passing. That's my frequency.
That's the triggers?
No, that's the Hall. The Hall is triggering the bipolar circuit.
Okay.
The magnetic field is generating the pulse you just listened to. The comparator is detecting the magnet passages of the coil, inductance-wise. So it generates a little bit of this, right?
Okay.
And the comparator sees that, and it steps itself up until it gets to the point, and then it goes dump. So it's doing three things at one time. It's looking at the output battery. It's looking at the capacitor in terms of voltage. And it's looking at the frequency of the wheel. Because if I stop this, if I slow it down, I'll change the number of steps to get there. All right, so no matter what speed I go, I want to be able to follow that voltage all the way to the top of the capacitor, and exactly at that point in time when the most current that I can develop in the terms of joules being delivered to the battery. And joules are energy. So I had to get here because the machine would not do it. The model would not operate like the big wheel. So the solution was to find the correct impedance by shifting coils around, and it took the extra coil here to do it. It's not part of the machine. It's just part of the impedance change, the same as this one. Now Eric's is going much slower than mine, and his rate to step up to get the energy is slower. Okay, what is it? Somebody said, okay, what is it? We discussed on the Energetics Forum, I discussed it, RS was there. I said to use a SIDAC. Do you remember that, RS?
Yes, sir.
And nobody could choose the right thing.
I never made it work.
Right? Was a suggestion, because then that device could look at the capacitor, and then the output from that device could fire the FET. Well, that didn't work too good. It punches through the gates of the FETs. So the solution to the problem was 3 independent voltage sources or current sources, Zener leveled. This one's at 15 volts. That's the one that's operating the amplifier. So if I got 200 volts out here, and I got the correct resistance here and the right Zener here, I'm only going to get 15 volts. That's why you see the 5-watt resistor in line, because the machine is generating more voltage than the circuit can handle. The next solution is a reference voltage. Once again, another Zener. And that's being applied, this reference voltage is being applied to this pin. Am I teaching electronic class or what? I'm sort of lost now. The next one is a free floating divider. divided by 2, right? 47K and 47K is going to divide by 2. The next solution to this problem to get the comparator to work would be what? Something to adjust it. Pot, 20-turn pot. The next problem is what range do we want it to work in? Oh, easy one. Another resistor in series to ground. Now you have a range. You change this one, this range changes. Then you must change the reference diode. So if I'm working on a 24-volt system, this is going to be 10 volts. Come on, we got some electrical engineers in here, don't we? Yeah, but he's falling asleep.
Taking notes.
You're taking notes? How could that be?
You're a professor. He has to take notes.
Is that right? Can't find anything wrong with that? Just smiling. Okay. So then the next problem, now does everybody understand that part of it?
No, but carry on.
Okay. All right, fine. So the next way to figure out what's there is to sum all these. Just sum them. Because it's just going to measure this. That's all it's going to measure. Right? It's just going to measure the cap. It's going to watch the cap go up. And when it gets to this level, depending on where you have set this pot, guess what? It goes up, green light turns on, opto turns on, capacitor dumps. Inverted across the battery for gain. Remember, we talked about the gain. So, next part of this switch. There's a lot more. In fact, I'm going to give you a little break in a minute. There's a lot more to figure in this one out. Oh, yes, there is, because number one, you got to be very careful of the FET under that capacitor dump, because you do not want to exceed the gate voltage. Or you're going to go into breakdown, and you're going to go into breakdown very quickly, and it's not pretty because the center of the MOSFET flies out and hits you in the eye, like the rock hit me. Good question, then, isn't it? What do you think the gate voltage is? Is it? Let's look at it. We have an optocoupler. I don't like going into all this math, so I do it the easy way. I just show you the circuit, go make it. The reference voltage taken from the IC is exactly the voltage that you need to drive the gate. So, now John could have got really complicated and put a voltage regulator in there. I hate gate drivers. It's the worst thing ever invented. It must be sitting right at the pins. where funny things happen. So I make my own gate driver. I use this voltage to drive the gate because I have all the drops there. I lose a little bit in this one, and I lose a little bit in this one, and a little bit in this one. So my circuit is inverted the way I've always done it, with the FET or the transistor. Minus terminal, plus terminal, potential across the battery, stair-step up, comparator switches, opto triggers. Guess what? Bang. And I never worry about blowing the FETs out because it never gets exceeded. Now, does that make sense? Because it's operating there. A lot of people like to put resistance in. That's okay. A lot of people like bipolar gate drivers and might want to put that, but you're just burning more energy when you do that. Okay, and this is burning enough of the energy to do it. But we have excess, so we can dump. You can see it. You have plenty of excess there. You have about 25, 30 volts that you're dumping across the battery continuously in these pulses that you see. So it's just bang, 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 batteries rising up to what Peter Linderman said yesterday, until the top of the curve gets to where it belongs, and then after that, fly a balloon. Take the hydrogen and fly a balloon. And that is the secret to the 3-pole motor that was sitting in here, that everybody said, he didn't tell us. I did tell you. Nobody was listening. So now, what is it that you don't understand? Now, the next portion of this whole thing is, what did he do with the motor? Remember, I said to you that it's not the same bipolar switch. Highly modified Medini code. Devices are selected, no heat in the switch. Eric happens to be running one in this box right here that's 2 inches by 2 inches. This one's a little bigger, you can see it. This one looks more like an amplifier when you look inside. That's why I put a plastic top on there. I hate these rumors on the internet. He hid it in the box, we couldn't see. He's lying to us. He had more wires in the coil. Oh, he did this because it made up this. No, they weren't here. They're assuming. They're not seeing what you're seeing. They're not walking up to it. They're not touching it. They're not looking at the scope. So do we want to see what the motor pulse looks like? The Bedini Gold switch has been highly modified through the use of selected transistors. Okay, come on. We'll get this one out of the way. Since there's all these secrets.
Is this a full pulsar setup, I see two transistor-looking things, but I didn't know whether they were in parallel or whether you.
They're
had
in
them.
parallel.
Okay, so it's not a two-stage; it's just a single stage.
Yeah.
Is there a primary and charging here, or two primaries on this one?
That's a bipolar switch. See the motor? Come on, you piece of... See it? See how the cap takes the pulse, the energy pulse, and it's being stepped up. It's going ding, 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 ding. There's no heat there, is there, in the box? Of course not. Hall effect.
Yeah, but that's what.
Boy, that's a crooked wheel. That's the most perfect wheel I ever built my entire life. But it's pretty.
The solenoids are in, the coils are in parallel, the second coil?
Yeah, they're in
So
parallel. All of them are in parallel.
changed like you had it, you had to add.
I had to add the inductance.
You saw like the impedance was very much capacitance?
No, it wouldn't match the capacitor, so I'd add inductance.
Wouldn't match the capacity.
Right, I do it like Tesla.
I don't know.
No, know him? You gotta read
I
about
don't
it.
know how, yeah, I read a lot. I don't know how he was doing it.
When he was doing it like that.
Makes a lot of sense to me.
I want to build it before.
Is this 12 or 24 you're running?
This is 12 volts. I'm running it at the lowest power that I can run it at. And if I was to run that at 20, 24 volts or 36 volts or 48 volts, I'm sure the wheel would just fly apart. Of which then it would have tremendous torque, and I'd have to slow that down somehow. It's got torque now.
You did a good job telling us how to do this, you know.
That was my job.
You did good, because mine came out okay.
Not like that, though.
Other than the SCR circuit, I did really good.
Yeah.
John, is there a name for this one? Do you have a different name?
No, this is a 3-pole. It's the same one as what they call the Ferris wheel. It's just a small model to demonstrate what the white boxes were on the, yeah.
Isn't the Tesla switch just stealing the surface charge?
No. Okay, that is the best explanation I can give to you without going any further of how to build this. That's what you have to do. You have to tune the system to the capacitor, and you have to use the correct voltage sensing device, which is really easy to do. It's in every book. It's all over the internet, is the comparator. And make the comparator work any way you want to make that comparator work. Don't try to make the comparator work with voltage regulators. Use the zener and the resistor is just fine. Otherwise, you're going to keep sucking current, thinking that you're making your circuit complicated. And yes, you are making your circuit complicated. Complicated into not getting anything into the battery. So just do it real simple. Don't try to complicate this. Now, what do you think is hidden? Right. So, when I go on the internet in 3 weeks, and Joe Brown said, I couldn't see in the boxes. Right. You weren't there. And as you can see, it doesn't make any difference if it's aluminum, wood, Whatever's there is there. I don't care if you make it out of cardboard, it will do the same thing. It's non-dependent on what this material is. So you could be the Flintstones, might be, and it would still work. And so would the SG. So there is a way to get energy when there is none. You can do it by using that and an oscillator. You can do the same thing with a solar panel using that comparator. Be very careful if you do that, as you will be eating the capacitor, especially with the type of oscillators. So anyway, thank you all for coming, and I'm glad I could tell you this.
Thank you.
Question, he had a question. Here, it's yours.
Yeah, the one question I had was if you could explain the wave on the scope exactly what we're seeing. I mean, we saw it, but I don't know what I saw.
Well, I drew it on the board. And I explained it. Stair-step up.
No, but I mean on just the latest display.
Oh, that was the motor wave that most are familiar with. And that one that you see coming down like that is the charging you're looking at as it builds energy down.
Okay.
The switching down.
See, if I had these running, I could be charging my batteries. Yeah, they'll be all right. I'll go slow.
You going backwards?
Not if I don't turn it on. Yeah, we can probably, just leave them on the table there for now.
Yeah.